Namaste, my friend, and welcome back to NEET Physics with Typical Monk. This is Class 4, and today we reach the beating heart of mechanics, the laws of motion. Sit with a small truth for a moment. Everything around you either stays still or changes its motion, and there is always a reason. A push, a pull, a tug. Newton gathered all of it into just 3 laws. When Rhea first met this chapter, she solved every problem in her head and kept getting them wrong. The day she learned to stop and draw a free body diagram, one body, every force on it, her answers turned clean and certain. And here is why this matters so much. This is the single highest yield chapter in all of NEET Physics. Master it, and force, friction, tension, and turning all bow to you. Take a slow breath. Let us begin. So what will you carry home from today's class? First, Newton's 3 laws. Inertia, the great equation force equals mass times acceleration, and the action-reaction pair that always acts on 2 different bodies. Second, momentum, an impulse, and the beautiful idea that momentum is conserved when no external force acts. Third, the free body diagram and friction, static, kinetic, and the limiting friction where sliding is about to begin. Fourth, tension and connected bodies, pulleys, blocks tied by strings, and the safe speed on a banked road. And fifth, the knee drills, a full work 2-block numerical, an assertion and reason on the 3rd law, a match, and a rapid quick check. Ready? One idea at a time. Let us start at the very foundation, Newton's 3 laws. The first law is the law of inertia. A body at rest stays at rest, and a body in uniform motion keeps moving in a straight line until a net force acts on it. Motion does not need a cause, a change in motion does. The second law is the engine of every numerical. The net force on a body equals its mass times its acceleration. Force equals ma. Give me the forces, and this one line gives me the motion. The third law, for every action there is an equal and opposite reaction. But hold this carefully. The 2 forces act on 2 different bodies, never on the same one. That is the whole secret. And underneath all 3 sits momentum, mass times velocity. Written P equals mb. Newton's real statement of the second law is that force is the rate of change of momentum. When Arjun pushes a wall and the wall pushes back, that is action and reaction. And momentum keeps the books balanced. Now look at this picture carefully, because it is how every mechanics problem is truly solved. This is a free body diagram, 1 block resting on a rough inclined plane, with every force on it drawn and resolved. First, the weight mg always points straight down toward the center of the earth. On a slope, we resolve it into 2 pieces, one along the surface, one pressing into it. The normal force N pushes out, perpendicular to the surface. And here is the trap. On an incline, the normal force equals mg cosine theta, which is less than the full weight, not equal to it. The component pulling the block down the slope is mg sine theta. Against it, friction acts up the slope, resisting the tendency to slide. And friction is not unlimited. It can rise only up to mu times the normal force. Beyond that maximum, the block gives way and begins to slide. Prior used to forget the cosine and set the normal equal to mg. The day she drew the incline properly, that whole family of problems opened up. Now let us meet friction properly. The quiet force that resists sliding. Static friction is the clever one. It adjusts itself to exactly match whatever force you apply, holding the body still. It can be anything from 0 up to a maximum. Push gently, and friction pushes back gently. That maximum is called limiting friction, and it equals μs, the coefficient of static friction, times the normal force. This is the threshold where a body is just about to slip. Once the body actually starts sliding, kinetic friction takes over, and it equals μk times the normal force, and μk is always a little less than μks. That is why the first shove is the hardest. And here is the surprise NEET loves. Friction depends on the normal force, not on how large the contact area is. A brick sliding on its side or its end feels the same friction. Rohan lost marks, assuming a bigger surface meant more friction. It does not. Time to solve a full NEET numerical together. Slowly, the monk's way. 2 blocks hang over a frictionless pulley, joined by a light string, one of 3 kg, one of 5 kg. Find the acceleration and the tension. Take g as 10 meters per second squared. Step 1. The given. 2 masses over a frictionless pulley, 3 kg and 5 kg, connected by a light string. The heavier one falls, the lighter one rises. Step 2. The setup. For each block, the net force equals its mass times the acceleration. The string is light, so the tension is the same throughout, and both blocks share one acceleration. Step 3. The acceleration. It equals the difference of the masses times g, divided by the sum of the masses. That is 5 minus 3 times 10 over 3 plus 5, 20 over 8, which gives 2.5 meters per second squared. Step 4. The tension. Look at the lighter block. The tension pulls it up, gravity pulls it down. So tension equals m1 times g plus a, 3 times 10 plus 2.5, 3 times 12.5. Step 5. The answer. The tension is 37.5 Newton with an acceleration of 2.5 meters per second squared. That is the whole part. Given, setup, acceleration, tension, answer. The very same method solves every connected body problem NEET can ask. Let us make the connected body idea permanent, because NEET returns to it every year. Here, one block rests on a table, and a second block hangs over a frictionless pulley, pulling it along. First, one light string means the tension is the same on both blocks from end to end. Do not give them two different tensions. Second, because the string does not stretch, both blocks move together with one shared acceleration. Solve for one and you have the other. Third, right force equals m for each. For the hanging block, m2z minus t equals m2a. For the table block, t equals m1a. Fourth, add the two equations and the tension cancels beautifully, leaving the acceleration equal to m2 dive divided by m1 plus m2. We have solved this in one line once you trusted the diagram. Draw it, tension common, one acceleration, add the equations. Now set up straight. These 5 lines are what NEET actually asks year after year. 1. Always draw the free body diagram first. One body, every force acting on it, and then force equals mass times acceleration. This single habit saves more marks than any formula. 2. Impulse equals the change in momentum. Force times time equals the change in mv. That is why a longer contact time means a gentle force, the whole idea behind airbags. 3. Limiting friction is μs times the normal force, and friction always opposes the relative tendency to slide. Its direction is decided by the motion, not by you. 4. On a frictionless incline, the acceleration is g sine theta, and the normal force is mg cosine theta. Remember, the normal is not the full weight. 5. The safe speed on a banked road is the square root of rg tangent theta. A car can turn on a frictionless bank at exactly this speed, no friction needed. Let us drill the NEET way. Remember the 4 options. Option I, both statements true and the reason explains the assertion. Option B, both true but the reason does not explain. Option C, assertion true, reason false. Option D, assertion false, reason true. First one, assertion. The action and reaction forces of Newton's third law never cancel each other. Reason, action and reaction act on 2 different bodies. Think like Ria, check each alone, then the link. Is the assertion true? Yes. Is the reason true? Yes. And does the reason explain it? Perfectly. Forces on 2 different bodies simply cannot cancel, because cancelling needs both forces on the same body. Both true. Reason explains option A. Second one. Assertion. A horse can pull a cart forward even though the cart pulls the horse back with an equal force. Reason. The horse pushes the ground backward and the ground pushes it forward. Both true, and the reason is the very cause. The forward push from the ground is what moves the whole system. Both true. Reason explains option A. Third one. Assertion, action and reaction, being equal and opposite, always add up to 0 net force on the system. Reason. The third law: forces are equal in magnitude and opposite in direction. Check the reason first. True. But the assertion is false because the two forces act on different bodies, so they can never be added as a net force on any one system. Assertion false. Reason true. Option D. A quick match now. Say each answer aloud before I reveal it. Newton's second law. Force equals mass times acceleration. The engine of every numerical. Impulse. Force times time equals the change in momentum. A large force for a short time or a small force for long. Limiting friction. M(s) times the normal force. The maximum static friction right before sliding. And safe speed on banking. The square root of rg tangent theta. The turning speed that needs no friction at all. If all four came to you before the reveal, this chapter is becoming yours. Here's a favorite new NEET format. I will read some statements. You silently count how many are correct. Statement 1. Action and reaction always act on two different bodies. Hold your verdict. Statement 2. The normal force on a block always equals its weight, even on an incline. Think carefully before you answer. Statement 3. Kinetic friction is slightly less than the maximum static friction. So, how many are correct? Two statements, the first and the third. Action and reaction truly do act on two different bodies. And kinetic friction truly is a little less than limiting static friction. That is why the first push is the hardest. But the second one falls. On an incline, the normal force is only mg cosine theta, less than the full weight. That single chap catches thousands, and now you will not fall into it. Now let me save you some marks. Two myths that trap thousands of students every year. Myth 1. Action and reaction cancel out, so a body can never accelerate. It feels so logical, equal and opposite. Surely they act on nothing? Arjun believed this for months. But here is the truth. The two forces act on different bodies, so they never cancel on the same body. Each body feels only its own force and can accelerate freely. Myth 2. The normal force is always equal to the weight of the object. On flat ground, it happens to be, so students carry it everywhere. The truth? On an incline, the normal force is only mg cosine theta, less than the full weight. And if someone presses down on the block, the normal grows larger than the weight. The normal force is whatever the surface must supply. Never assume it equals mg. Time to test yourself. Rapid fire. Here is the rule. I ask, you answer in your head before the reveal. No pen, no paper, just a free body diagram you built today. Question 1. What is the force on a 2 kg mass accelerating at 5 meters per second squared? Force equals ma 2 times 5, 10 Newton. Question 2. What is the acceleration of a block sliding down a frictionless incline of angle theta? It is g sine theta, only the component of gravity along the slope. Question 3. What is the limiting friction if mass is 0.4 and the normal force is 50 Newton? Mass times n, 0.4 times 50, 20 Newton. Question 4. What is the impulse when a 100 Newton force acts for 0.2 second? Force times time, 100 times 0.2, 20 Newton second. And question 5. What is the momentum of a 4 kg body moving at 3 meters per second? Mass times velocity. 4 times 3, 12 kg meter per second. If those came quickly, you have truly understood today's class. Let us gather the whole class in one slow breath. Newton gave us 3 laws. Inertia. The equation force equals mass times acceleration. And action-reaction, which always acts on two different bodies. Force is the rate of change of momentum, and impulse, force times time, equals the change in momentum. Always draw the free body diagram first, then resolve. And remember, the normal force is mg cosine theta on an incline, not the full weight. Friction rises only up to mu times the normal force. And once sliding begins, kinetic friction takes over. Connected bodies share one acceleration with a common tension, and when no external force acts, momentum is conserved. And next class, work, energy and power. The work-energy theorem, conservation of mechanical energy, and collisions. Do not miss it. And so, my friend, we have reached the heart of mechanics. It may have looked like blocks and strings and inclines, but understand this. The laws of motion are the glamour of every force problem you will ever solve. Every pulley, every car on a bend, every rocket, every collision, each one begins with a free body diagram, and the line force equals mass times acceleration. Ria, Arshan, Priya, and Rohan all struggled here first, and all came through by trusting the diagram. Be patient with yourself. Tonight, redraw the inclined free body diagram once, slowly, and feel the forces resolve. One idea at a time, you will crack NEET. Of this I am certain. If this class brought you clarity, subscribe to the channel so the next one finds you. Until then, keep going. I will see you in the next class.